Good afternoon all. Myself Rajit TJ, Assistant Professor Department of Civil Engineering, Vardhavardha College of Engineering, Mysore. I welcome you all of you for the session 1 of Day 6 GATE training program on subject Soil Mechanics by Professor Chethan L. Professor Chethan L working as Assistant Professor having over 3 years of teaching and research experience, and he obtained his bachelor's degree in Civil Engineering from KVG Surya and master's degree in Geotechnical Engineering from East West Institute of Technology, Bangalore. His areas of interest are advanced foundations and earthquake engineering. He also offers consulting services in geotechnical engineering. So in today's session, we will be speaking on soil mechanics. With this short note, I request Professor Chethan to take over the session. Over to Professor Chethan.
Thank you, Rajit sir. First of all, good afternoon, everyone. So today we are on day 6 of session 1. So Rajit sir, please confirm whether my presentation is visible. Yes, thank you, sir. Okay. So welcome you all for the day 6 session 2, especially on soil mechanics. So here it goes. As we studied in the previous session, that is session 1 of soil mechanics, we come through some of the basic analysis of Pareto principle, saying that if you study the 20% of the syllabus, you can get 80% of the marks. Then we have analyzed some of the basic details regarding the previous year analysis. We have done it, and we have taken some of the important topics, especially in important subjects, and we have studied some of the analysis where the particular subjects has give the more importance, right? So then we have to come up with some of the distribution of marks for the dividing of the strategies. These are all the things we have been discussed in the previous session, that is in session 1. So if you didn't look at the previous video, please go and watch the video for more information. Okay, so as we talked about in the previous session, we have covered the first 3 topics, that is properties of soil, classification of soil, and clay minerals of the soil. So now today I will be talking to you about compaction of soil, effective stress, permeability, as well as even the seepage analysis of the soil. If time permits, I will move on to the shear strength of the soil. And anyway, as I informed in the previous, so the foundation engineering topics, that is all the advanced topics of the geotechnical engineering will be covered by our HOD, that is SK Prasad sir, in future sessions. Okay, so this is my content. These are the things we are going to discuss today. So basically there are 5 major topics. That is, one is the preparation is the main key for getting into any examination or clearing it. So but then I will be talking about what is compaction and what are the important things we have to be keep it in mind while facing the compaction problem. Then total stress, effective stress, and pore water pressure. Also I will be talking to you about the seepage analysis, flow net, and the other things. At the end of all these 4 topics, I will be talking to you, and I will be taking you to the previous year's question paper, where all the questions which have been asked from the past 27 years, I will try to cover it as much as possible. Okay, let me go to the first one, that is the preparation is the key. As you all know that if you go to anything, either it might be a game or either it might be a life, anything, you won't get anything in life that you fight for, but whatever you get, it's always a fight, right? So remember that. So whatever you want to get, it's always a fight. So don't give up on anything. Don't face anything in life by putting a doubt in your head or in your mind, right? So if you want to win in some game or win in any of the thing, so if you already have a doubt in your mind, you can't do that. So if for that, how to overcome the doubt? To overcome the doubt, this is the key. There is no shortcut to success. The success can only comes through the hard work. So that is the key for preparing in GATE exam or any of the exam. You use it. So as I mentioned about the second one, I will be talking to you today, which is about the compaction. What exactly mean by compaction, right? As the term itself indicating, compacting any material. Here we are talking about the soil, so I will be talking about compacting the soil. Basically, compaction is all about, it is a mechanical method of improving the property of a soil. You can observe here, that is, if the loose soil, if you put some compaction energy, right, along with the water will act as a lubricant to help or to improve or to compact the soil. So finally, at the end of the day, we will get the compacted soil. So what we can say, it is a mechanical process where the water the water has been added as an additive to get the more compacted soil. Simply, you can solve it as it is a ground improvement technique where the soil has been densified through external compactive energy. So here you see before the work, that is the loose soil, then after the work, that is after you have been added with the compactive effort, you will get the soil like this. Okay, what is the basic principle which is involved in compaction? If you understand the principle that which involved in compaction, so you can easily get at least 1 or 2 marks in the particular exam. Rather than that, if you understand the concept in any examination, you can get a marks. The concept is simple. What is the principle which involved? As we know that if we want to get the densified soil, we have to compact the soil, that is loose soil, by adding some compactive energy with the water, right? So here also, it has been explained with the graph saying that here you see, let me take, and here you see, when we start, keep on the graph which has shown, which is regarding the water content along with the dry density of the soil. As we keep on adding the water content to the soil and we keep on increasing the compactive effort, the dry density of the soil will keep on increases. It will keep on increases up to certain limit, then it will start to decrease. That is the basic principle. But how it will take place? Example, as I mentioned about, when the loose soil has been started lubricating, that is when you started adding the water to it, whatever the dry soil which is there, it is having a void which has been started filling up with the water, and the lubrication process will take place. When the lubrication started taking place, whatever the soil particles which are present in the particular soil, it will going to reorient itself, because there is an amount of compactive effort which is lying over it, right? As the process keep on continues, all the soil particles which are present in the soil will get completely compacted and completely reoriented, and the voids have been filled with the water content, and it will be provide the more densification, providing a lubrication. Then it will reach up to a optimum point. Once the optimum point has been reached, that particular optimum point, with respect to the point, if whatever the density, dry density you will obtain, it will be called as a dry density of the soil, and the particular moisture content is called as optimum moisture content. And once the optimum moisture content has been reached for a particular compactive effort, then the soil is going to keep on decreasing its density of the soil, because the water content will keep on increases. The water will predominate the amount of soil particles, or else you can call it as the volume of the water will be more compared to the volume of the solids. As the volume of the water increases, obviously the water will start to lose its particular capability. So that's why the density of the soil will keep on increases. But one thing we have to observe here is that whatever the optimum percentage of void ratio, optimum percentage of dry density or optimum moisture content we will obtain, it is always equal to almost nearer to the 100% saturation of the soil. But in practically, it is not easy to get 100% saturation in soil, but always whatever the achievement of maximum dry density can be achievable, which is nearer to 100% saturation. Right? And one more thing we have to observe is that whenever we have started increasing the water content to get the desired dry density of the soil, you see here the flocculated structure of the soil will going to orient itself into a dispersive structure. As we study in the previous class regarding what do you mean by flocculated structure and dispersive structure. In flocculated structure, we know that the permeability of the soil will be more because it has its irregular orientation. When you keep on adding the water, you can observe here, when you keep on adding the water to the particular loose soil, this is a loose soil. When you keep on adding the water to the loose soil, the water will try to enter into the voids. You can observe here. It will enter into the soil, and even though if you are providing the compactive energy to the particular soil, it will try to get more and more compressed. As the soil is getting to more and more compressed, which increases the densification of the soil, and at one point, that particular point we called as the optimum point. At the optimum point, the amount of the voids which has been completely started to fill with the water, and the amount of whatever the quantity of the air which are present, it is almost equal to the zero. When we reach that particular amount, we will obtain the optimum dry density as well as optimum water content. And also we observe that the reorientation of the structure will take place here. Whatever the flocculated structure of the soil particle which was present in the initial or in the beginning, it will going to reorient itself. When they start to reorient themselves, always we can expect the more densified soil, right? So after, if you keep on increasing the water content, whatever the densified soil which was present at the optimum content, it is again going to be very free. When they started to be releasing the compression stage, so again the amount of the density we can achieve will be the reduced, or it will be a minimum. So the important point we have to remember here is that we can able to achieve the maximum optimum moisture content and optimum dry density when the saturation which is very near to the 100%, and the structure will always changes from flocculated orientation to the dispersed orientation by indicating the high permeability or high permeability at the beginning to the amount of reducing permeability at the end. Along with that, here we observe that there is only a compaction is meant for the evaluation of the air content. It is not for the water content. Here the voids, whatever the voids which have been there, it is started filling with the water. When it is start filling with the water, the density of the soil will going to increase. So that is the three major key points we have to observe in principle of compaction. As we all know that whenever we talked about the principle of compaction, basically this is the graph which basically have a high importance in any of the cases, because whatever practical applications we have been doing, it is only applicable on this particular graph, right? So what exactly this graph shows, it's the compaction graph or compaction curve, we can call it as. Here you see, this is the point where we can obtain the optimum moisture content and optimum dry density of the soil. If the soil which has a optimum moisture content, and if it is at the dry of optimum, it can be exactly divided into the center where the optimum dry density has been obtained, and the left side of the part which is called as dry of optimum, because at the dry of optimum, the soil which has a ability to absorb the water, which has an ability to lubricate, right? So once it has been reached the particular point, it has been completely lubricated and it has obtained its maximum dry density. Next, it will move on to wet of optimum. That is when the soil has been moving to the wet of optimum, the amount of the dry density will keep on decreases even though increase in water content. So wet of optimum, the optimum, it is a division. The division is the point where we can get the optimum dry density and optimum moisture content, where towards the dry of optimum, always the soil has an ability to absorb the water content, and towards the wet of optimum, the soil doesn't have an ability to absorb any amount of water. But one thing we have to notice here is something I have written is as zero air voids line. What exactly mean by zero air voids, or what I exactly mean by 100% saturation? As I'm talking about, we can achieve the maximum amount of density and the water content at particularly the saturation of which is nearly equal to 100%. When the saturation is nearly equal to 100%, then is it not possible to achieve the 100% saturation? It is very difficult to achieve the 100% saturation in practical, but as through the observation of the graph, we can plot the 100% saturation curve. That 100% saturation, which indicates the amount of air content, is zero. Because as we studied in the previous class, saying that whenever we are talking about the volume of the voids, either we have to talk about the water content, or we have to talk about the air content, or the mixture of both. If the 100% has been completely saturated with water, then there is no amount of air content. The air content will be zero. The 100% saturation line is the line where we can expect the entire voids of the soil has been completely filled with the water. Okay, so but when it comes to, if you want to calculate any some percentage of the air void line, example, if you want to calculate 50% of the air void lines, you can take 50% of saturation and 50% of air content. Okay, how to calculate the 50% or 100% saturation line, which is also called as zero air void line. So the air void which has been zero, that particular line is called as zero air void line, and it's also called as 100% saturation line. When the soil is in 100% saturation line or it is in zero air void lines, you can observe I have taken one simple diagram here which shows that whatever the soil particles which are present here has been completely compacted, and the amount of space which is present in orange color, which indicates the void space, and it has been filled with water. So how to calculate the zero air void lines when the saturation is there and when the water content is there? Let me see it here. Okay, before that, before going to the problems, let me take you through a small things we have to remember. Sometimes they will ask the question based on this. That is, whatever the principle we have been studied, the principle has been taken by the Proctor. In 1938, Proctor has given a relationship regarding there is a difference, there is a relationship between the amount of soil along with the variation of water content, and he decided to give the particular methods to calculate the compaction in the field as well as in the lab. So basically, we know that there are two tests has been taken to calculate the compaction in the field as well as in the lab. That is basically, first one is the standard Proctor test and second one is the modified Proctor test. What exactly mean by standard Proctor or modified Proctor test is all about the procedure for both standard Proctor and modified Proctor is the same, as you already know that, but here the difference is the difference will vary with the compactive energy. The hammer used in the standard Proctor is of 2.5 kg, and in case of modified Proctor test it will be 4.5 kg of the hammer, and the volume of the mold will be 1000 cc, and we know that the hammer which will be falling at a height from basically in 30 centimeter in standard Proctor and 45 centimeter in modified Proctor test. Only variations we have to observe in both the standard Proctor and modified Proctor is the compactive energy along with the number of layers which has been used to compact, right? So it also basically relates to the compactive energy, with saying that in standard Proctor we basically go for 3 layers, in modified Proctor we'll go for 5 layers with increasing compactive effort. So this is the diagram which shows the components which has been used for the particular compaction test, and we know the standard procedure which has to follow according to BA standards for both standard and modified Proctor test. But here is one important point we have to note down about. Sometimes they will ask the question based on that. That is how to calculate the compactive energy, or there is always a question which is relating to the compactive energy. So how to calculate the compactive energy, or how to relate the compactive energy? To relate the compactive energy, that is E equal to NNWH by V. So this is we have to remember. What do you mean by N? Number of blows per layer. Or how many number of blows we are going to provide in each layer? That is 25 number of blows in both the test. Then what is N? N is number of layers. In standard Proctor test, we are going for 3 layers. In modified Proctor test, we will go for 5 layers. What is the weight of a hammer? The weight of the hammer we are going to use in standard Proctor is 2.5 kg and modified Proctor is 4.5 kg. And when it comes to W, that is hammer weight. Then when it comes to height of drop, the free fall of the hammer in a particularly in terms of the standard Proctor is 30 centimeter and in modified Proctor it is 45 centimeter. Then volume of the mold we basically preferably use to go for 949 cc, or sometimes we can also consider it as a 1000 cc. So this is the equations we have to remember to calculate the compactive energy or anything which is related to compactive energy, that is E equal to NNWH by V. So as we all know that when we are talking about the compaction, it's all about considering about the density of the soil. To calculate the bulk density of the soil, basic thing we have to know about density equal to mass by volume or weight by volume. If it is a dry density, we have to relate it with the dry weight along with the water content. But when we are going for a compaction curve, when we are using the compaction curve, dry density can be calculated by using gamma W divided by 1 plus W. So we can go through that. But if you are using for a 0 air void line, or if you are using for the amount of air voids, so how to calculate it? That is gamma D can be calculated by using 1 minus Na into G into gamma W divided by 1 plus WG. Here the Na indicates the amount of air voids. Example, as I said, the 50% of the air, multiply or substitute all the time the 50% of the air, will get what is the amount of drying density at 50%. If you are going for calculating the maximum density by considering the percentage of air voids is equal to 0. That is, if you have taken a maximum dry density at 100% saturation, which can be calculated by using Z equal to, that is gamma D maximum, theoretical maximum. The theoretical maximum dry density can be calculated by using G into gamma W divided by 1 plus WG. Remember this. So why I am telling, because always there is a question from 0 air void lines. So remember that. Now, how the compaction will affect on the soil. So sometimes one questions will be there based on how how the parameters which has been affecting the compaction, and what are the factors which is affected by the compaction. Basically, we know that the soil structure, the water content, permeability, then the amount of compactive effort, the type of soil is. These are some of the parameters which basically influenced by the compaction, as well as they are the one which is influencing the structure of the soil. So we know from the basic principle of the compactions, we saw that always the soil structure of the soil structure will go to vary as the compaction. We started increasing the compaction. That is, you see here, if I take on the first graph here, the flocculated structure has been completely, as keep on increasing the compactive effort, or as the density of the soil has been keep on increases, what will happen? The flocculated structure will get into highly dispersive structure. So whatever the irregular orientation of the flocculated structure, as we keep on adding the compactive energy to increase the density of the soil, it will get into reorient themselves by reducing the permeability of the soil, and they are going to more densify. So the flocculated structure will going to completely divert into dispersive structure by reorienting themselves due to the addition of external agency. Next one, how the different types of soil, how the soils will be affected due to the compaction. The soil will be affected due to the compactions. We can see that here. You see there are different types of soils are there. The well-graded sand, sandy clay, low plasticity clay, high plasticity clay. You observe here, as the soil is getting finer and finer, it requires the maximum amount of water content to achieve its own maximum density of the soil. So the type of the soil will also basically depend on compaction of the soil. Here, the coarse grained soil will always possess a maximum amount of density compared to the fine grained soil in lower water content. That we have to remember. Always the well graded soil or the coarse grained soil have possessed the maximum amount of their density with the lower amount of optimum moisture content. To get the maximum amount of dry density in a clay soil, we have to go for maximum amount of water content in the fine grained soil. So as we know that the zero airwide lines will always appear for any type of the soil you consider, always the zero airwide line will appear on the outside of the curve, because we cannot get the 100% saturation, as well as it is not easy to remove the 100% air in any of the soil because it is existed in nature. Right? So next one, how the compactive effort of the soil, how the compactive energy we are providing to the different kinds of the soil will affect. Example, you see the compactive effort. When I'm talking about the compactive effort or compactive energy, it is all about how much amount of the load we are putting on a particular soil to get the desired density. Right here, you see there are different types of the compactive effort: 20 blows, 50 blows, 30 blows, 25 blows. As you observe that, as increasing the number of blows, as increasing the compactive energy in a particular soil, the optimum moisture content line will always shift left side towards the curve. Why? Because the moisture content we can obtain through increasing the number of compactive effort in a lower water content. Example, if I consider the first and the last curve, to get a desired density of the particular 20 blows, in a 20 blows, I have to achieve a moisture content to this much level. But when it comes to 50 blows, if you are providing the compactive effort of 50 blows, you can achieve the same density, even higher than the same density at lower water content. So always the compactive effort plays a very important role. If you increase the compactive effort, you can desirable to get the lower optimum moisture content with higher amount of dry density of the particular soil. Next one I will be talking about the permeability, how the permeability will affect. As you observe here, as keep on increasing the density of the soil, the permeability of the soil will keep on decreases. We know that any soil, remember one thing, any soil which has a permeability which is greater than 10 to the power minus 9 will be considered as impermeable material. So here also, here you see I have taken for 10 to the power minus 9, as keep on increasing the density of the soil. As we keep on increasing the density of the soil, the permeability of the soil will keep on decreases until it reaches its maximum value. Once it has been reached its optimum stage, the amount of water in a particular volume of the soil will be increases, and then again the permeability will start to increase. Okay. Next, when it comes to the compressibility of the soil, what exactly mean the compressibility? What is the amount of the compression, the rate of compression we can expect from a particular soil, it's called effect of compressibility. So how the compressibility has been getting affected by the compaction, we can see in the diagram. Here you see, if it is an undisturbed soil with low pressure condition, it will be very less affected compared to the same soil has been remolded. The same soil has been remolded with undisturbed soil, it will have the more amount of compressibility. So if the remolded soil has an ability to again rebound themselves, and to rebound themselves, we have to provide a high amount of the pressure. So that is regarding compressibility. Next, when it comes to the shrinkage, how exactly the shrinkage will affect the compaction? To know that, here you see the entire compaction principle has been divided into two sides. We know that at the optimum stage, we have to divide the particular soil into two things. That is, one is dry of optimum and another one is wet of optimum. In the dry of optimum, what will happen when if any soil which is we are achieving the optimum dry density in the dry side, which have a higher amount of swelling potential compared to higher amount of shrinkage potential. Why the higher amount of swelling potential will be more? Because at the dry side of the optimum, the soil, whatever the soil have a voids, it has an ability or it has a tendency to absorb the water. When it is absorb the water, obviously it has a high amount of tendency to swell, right? But when it comes to the wet of optimum, what will happen? The soil has been already completely, whatever the voids which are present, it has been completely filled with the water. All the voids have been completely filled with water. So now, if you allow the water to change, it is having ability to shrink more, because it can completely allow the water to go out of the particular soil shape. Remember, always in a dry side of optimum, the swelling potential will be more, and in wet side of optimum, always the shrinkage potential will be more. Why the shrinkage is more? Because on wet side there will be a more amount of water in the voids, so it can able to allow the water to flow out. But when it comes to the dry side of the optimum, the soil has an ability to absorb the water, so it will be having it will absorb the water, and then it's going to swell. So the swelling potential will be more, right? So that is what written there. Next, so that is the second topic that I have been completed. The next one will move on to the effect, total stress, effective stress, and pore water. So what do you mean by total stress? As the term itself, see, this is the important topic where you can expect more than 2 to 3 marks, and it is if you understand the concept, it's very easy. So concept is very simple, fine. So now, what is total stress? The total vertical stress acting at any point below the ground surface is due to the total weight of everything which is lying above it. Example, here it is, if I want to know what is the total vertical stress at this particular point, it is the stress which has caused by any material which is lying above it. Okay, either it might be soil, water, and surface loading, anything. The total stress, we can calculate the total stress by using what is the unit weight of the particular soil with respect to the depth. Okay, so that is gamma W. So sorry, if it is a material is having unit weight gamma, then gamma into Z, which gives the total stress of the soil. So basically, while taking the unit weight of the soil, if it is a dry soil, basically the dry soil have an ability to obtain. It's having an average of around 17 to get around 18 to 23 kilonewton per meter cube as an average of around 20 kilonewton per meter cube. And if it is a water, we basically used to consider 9.81 kilonewton per meter cube according to the standard. So it's sometimes it's approximately used to consider 10 kilonewton per meter cube also, if there is no any mention. Always remember, the saturated unit weight has a highest amount of unit weight compared to the dry soil. Now, what is total stress? Total stress is all about the stress which is coming from the above lying material. Either it might be soil, water, or anything. We can easily calculate by multiplying the unit weight of the soil with the amount of depth which has been occurred. We know that when we are talking about the total stress with different kind of material, obviously there will be existence of different kind of conditions in the soil. So what is the different kind of condition? The first condition I'm going to consider here is that the total stress in homogeneous soil. We know that homogeneous means it's a unique soil where every property will be satisfied. But here, how to calculate the vertical stress when they have given in the problem, if they have mentioned homogeneous soil, to calculate the vertical stress you can go for by sigma v equal to unit weight of the particular material, that is unit weight of the soil into its depth. Okay, for the same thing, if they have given along with the river or a lake, if any water body which is presented above, that is either it might be a river or below, then the total stress we can calculate by sum of the weight of the soil which is up to the particular surface and the weight of the water above this vertical stress. So what is the amount? What is the sum of the weight of the soil which is presented till the surface of the soil? Then above that, what is the unit weight of water? How much water which is present above that? You can see here the sum of the weight of the soil up to the particular surface and the weight of water which is present above the vertical total stress at a depth of Z. So if the soil, if any particle which is located here, to calculate the total stress at this particular point, we have to go with by considering what is the unit weight here plus the unit weight of water to the particular depth. Next, if you move on, if it is not only homogeneous soil, it is not only soil along with the water. If the number of different layers, if the different layer of the soil is present, how to calculate the total stress? To calculate the total stress when there is a different multi-layer of the soil which is present, the total stress at any depth, the total depth, that is Z, it will be equal to sum of all these three. So how to calculate that? That what vertical stress sigma v equal to the first one. The first one, that is gamma 1, unit weight of the first layer with its depth, unit weight of second layer with the depth, plus unit weight of the third layer. The third layer is where it has been located. But here we have to deduct what is the weight which is coming from here. Right? So that is sigma 3 into the total depth. The total depth is Z minus D1 and D2. So this is the height. Right? So if the multi-layered soil which is present, if you want to calculate the total stress in that, you take the summation of all the three layers along with, remember, we have to consider unit weight of a particular layer along with at what depth it has been located. Right? If it is an unsaturated soil, we are talking about homogeneous soil, we are talking about a saturated soil, we are talking about multi-layered soil. What about unsaturated soil? If any unsaturated soil, what do you mean by unsaturated soil? If any soil which is presented above the saturated material, above the saturated soil, we can call it as unsaturated soil. Example, you can consider here, you see in the right side here, the up to this level, the soil which has been completely saturated with water. What about the voids which are present in the soil which has been completely saturated? But above, over it, there is a ground surface, above the top. But in between that, there is a layer. The layer which has been laid or which has been sandwiched between the ground surface and the saturated soil. It is called unsaturated soil. All the amount of the voids which has not been completely filled with the water, right? So how to calculate the total stress in that? To calculate the total stress in that particular constant, we have to go for taking the total vertical stress equal to unit weight of water with what is the height, okay, plus what is the unit weight of the particular this layer into the height, that is Z minus ZW. Okay, so that we have to consider for calculating the total stress at unsaturated soil. Now, we are talking about if the soil is homogeneous, if the water is present, if the lake is present, and if it is an unsaturated soil, how to calculate the total stress? If it is surcharge charge is present, if surcharge load is present, how to calculate the total stress? To calculate the total stress when there is a surcharge load, if there is any surcharge load, to calculate the particular vertical stress due to the surcharge load, we can go for the equation, that is the total stress equal to unit weight of a particular soil into its depth plus the surcharge load. What is the amount of surcharge which is coming above the soil? That we have to consider. But sometimes what will happen in terms of strip or fat foundation, the vertical total stress will decreases. both in depth as well as in horizontal distance. Then how to calculate? To calculate in that particular conditions, we have to go for using the Boyce-Inglis equations of distribution of the load. We know that according to the Boyce-Inglis, as we keep on moving towards the downward direction, the intensity of the effective stress will keep on decreases. That conditions we have to consider in terms of the strip as well as pad foundations, right? So next, the most important and most dangerous one is the effective stress. Why it is most important? Because any failure of the soil which is takes place, it is always influenced by the effective stress of the soil. Now, what do you mean by effective stress? Basically, the effective, we talked about completely about total stress. What is the total stress? Now, what is this effective stress? This effective stress is basically the stress which is balanced between the pore pressure and the total amount of stress. To define it, the difference between the total stress and the pore water pressure is called as effective stress. Example, here you see we have considered a small soil surface. In the soil surface, what is happening here? The sigma, which indicates we are distributing the load above the soil. When you started distributing the load above the soil, what will happen? Whatever the soil particles which are present inside the soil mass, along with the void space which has been filled with the water, that particular thing we call it as a pore water. The water which is filled the pores, which is called pore water, and the solid particles which is experiencing the load, the entire load which is distributed on top of this particular layer, now it has been taken care both by water as well as the solid grains. You can observe here, you can observe the blue color arrows, you can observe the black color arrows. Whatever the total stress, let me take it as, let me assume around 5 ton load which is coming above the soil. All the 5 ton which has been taken by 1 meter thick soil layer, 1 meter thick gravel, which has been completely taken the load by with the help of both the individual solid grains as well as the water. The water is also a main important key parameter to resist the load which is coming above the particular soil material. What happens if the soil escapes? What happens if the water escapes? We know that due to a number of conditions, always there will be escaping of water and entering of water. How it will change? When there is a escape of the water, all the loads which is coming above the particular layer has to take by the individual soil grains. Whenever it enters, what will happen? It will create its own pressure. That particular pressure is called pore pressure. It will try to lift up whatever which is there above it. Right? How to deal with it? So to deal with that, so we have to know about the effective stress. The effective stress is basically indicated by sigma dash, and the total stress which is indicated by sigma, and the pore pressure which is indicated by U. Right? So the measurable effect of the change of stress, such as compression, distortion, and change of shearing resistance, are due to exclusively to change in effective stress. That's why it's told the major important parameter in the changing in behavior of, especially changing in engineering behavior or characteristics of a soil, the major thing or major drawback is effective stress. If there is a variation in effective stress, it will always cause the variation in compression, distortion, settlement, and shearing, and even lot of things, right? So how to evaluate that? To evaluate that, we know that the effective stress, it's always equal to total stress minus pore pressure, because the total stress is the stress which is caused by any loading material, but it has been taken by both the effective stress as well as the pore water, right? So both the effective stress and pore pressure togetherly, they are taking the total stress which is coming over it. So if you want to calculate, what do you mean by total stress? Total stress equal to effective stress plus pore water pressure, right? So that is what we have to know. Next one. So if I move on, that is some of the points we have to keep in mind while analyzing the points on effective stress or the total stress. What are that points? If both the total stress and the pore pressure change by the same amount, the effective stress remains constant. If the amount of pore pressure as well as the total stress which is changed in an equal quantity, then there is no change in effective stress. The change in effective stress will cause a change in strength and change in volume. If there is a change in If there is a change in effective stress, it always changes the strength. That is what I mentioned about engineering properties of the things will change when there is a change in effective stress, right? Change in water table below the ground level. If remember here, changes in result in change in effective stress below the water table. Remember, changes in water level below the ground results in change in the effective stress below the water table. But same way, changes in water level above the ground do not cause any change in effective stress in the ground. Okay, so one thing we have to remember, if there is any change in water level that is below the ground, which always affects the effective stress in the water table. But if there is a changes in water level above the ground, if there is a change in water level above the ground, then it will not cause any changes to the effective stress in the ground below. So there is a effective stress, that change in effective stress, it will be taken as the total stress minus pore water pressure. So if you observe the failure condition in the right side, that is stress versus shear stress. Here you see there is the change in effective stress and normal stress can be observed with change in the effective stress. Okay, next, the another important point we have to keep it in mind is the rate of change of effective stress under loaded foundation when once it has been constructed will be same as the rate of change of pore pressure, as the rate of change of pore pressure, and it's controlled by the permeability of the soil. Okay, if the pore pressure in soil slope increases, the effective stresses will be reduced by the particular change in effective stress, and the critical strength of the soil will be reduced, sometimes leading to the failure. But the settlement occurs as the volume of the soil layer changes. The volume of the soil layers changes, which increase in change in permeability of the soil, which results in settlement. The settlement rapidly occurs, especially in coarse grained soil compared to fine grained soil, because the coarse grained soil have an amount of high permeability compared to the low permeability of the soil. Next one, the important topic we have to observe here is that how the volume of the soil will take place, how the volume of the soil will change. Here is the first diagram which shows when the soil is in equilibrium, the total stress or the effective stress, which is equal to total stress minus pore water pressure under equilibrium condition. We can observe here there is no volume change. The initial volume we have taken as V naught, and the total stress as sigma naught, and the change in stress as effective stress as initial effective stress as sigma dash naught. But as the amount of water or the pore pressure when it is enters, there is a change in amount of delta U. When there is an amount of change in delta U, then obviously there is an amount of change in delta sigma. Right, so whenever there is a pore water, enter or exit of pore water, which always cause the effect of changing its total stress. When there is a change in total stress, how much amount of the volume we can expect it to change? We can see here the total effective stress which has been changed due to the entry of the additional delta U, which is equal to delta sigma dash, which is equal to delta sigma minus delta U. If it is equal to 0 only after the loading, right? You can observe here the soil is same, but here the volume change will takes place whenever the total stress has been increased to delta H, right? So next one, we have been talked about total stress, we have been talked about effective stress. The next, another important parameter here we have to talk about is pore pressure. What do you mean by pore pressure, or what do you mean by pore water? Right, so what is mean by pore pressure or pore water? The water in the pores of a soil is called pore water. The pressure which is caused by this particular water is called pore pressure. The water which is present inside the pores of a soil is called pore water. The pressure within this pore water is called pore pressure, or the pressure which is exerted by this particular pore water is called pore pressure. Right. So what exactly mean by hydrostatic pressure? Which means that whenever the hydrostatic condition which exists, that is whenever the water level or water flow in the soil which is at 0 in condition, the pressure which is exerted at a given point which is which is called as an hydrostatic pressure, which is equal to U equal to gamma W into HW. As we know about to that, here also the pore pressure or the hydrostatic pressure can be measured by using unit weight of water along with the what is the height of the water in that particular case or in that particular soil. The natural static level of water in the ground is called water table or the periodic surface. Remember here we so many times used to call it as water table, groundwater level or periodic surface, which basically means that the static level of water which is present in the ground, there is no change, there is no variation in the amount of groundwater. The natural static level of water in the ground is called the water table or the periodic surface, which is called groundwater level. It is measured relative to the atmospheric pressure. Always we know that the periodic surface or the water table has been measured with reference to the atmospheric pressure because we are considering at the static level. Okay, so remember, whenever we are talking about a pore water or pore pressure, is the water which is available inside the voids. If it is causing a pressure, that is called pore pressure. How to measure this pore pressure or hydrostatic pressure? We can be measured by using the unit weight of water, which will be multiplied with the depth of water which is present in the soil. Then to know about what is the groundwater table or water table, it is basically the static level of water which is available in the ground. It is called the periodic surface level or groundwater level or groundwater table. It is measured relative to atmospheric pressure. Remember that. Next, how this pore pressure will vary, what are the different conditions we can expect, right? So example here you look at, whenever we taken a condition where the negative pore pressure exists, where when we can expect the negative pressure to be present, when there is a saturated soil which is present below some particular depth. Let me consider it as plus H. For this particular depth, the soil has been completely saturated. When it has been completely saturated, we can expect the positive pore pressure. After it has been saturated, then there is a development of the negative pore pressure, because whatever the amount of soil which is present above the water will have a tendency to absorb the water, right? So, and it will create the suction head at the particular point, resulting to the negative pore pressure. So that is below the water table, the pore pressure is always positive because the entire pores has been completely filled with water. But in dry soil, the pore pressure is zero. There is no amount of water in a dry soil. Therefore, the pore pressure is zero in dry soil. In the soil which is present below the water table, the pore pressure is positive. What about if the soil which is present above the water table? When the soil is saturated, the pore pressure will be negative because the total amount of pore pressure will lead to the negative rise of the amount of water inside the soil mass. This particular rise we basically call it as the capillary rise. We talked about the dry soil, we talked about the soil which is completely saturated, we talked about the soil which is present above the particular water table. But what about partially saturated soil? The partially saturated soil is basically composed of two important components. One is called the pore water pressure and pore air pressure. Because in partially saturated soil, we know that there is a amount of space for both the air as well as the voids. The air as well as the water, both will going to exert a pressure which is called pore water pressure as well as pore air pressure. Now, what exactly mean? What we are talking about is the water table. The water table is basically all about the amount of or the level of water which is present below the ground surface. When there is no flow which is taken, you can observe at the right side, when there is no flow which is taken place, the water surface will be at exactly at the same level in all the standpipe. If there is no flow, you can observe here, you can observe this sky blue color, right? So the water level is same in all standpipe below the ground level. That particular thing is called hydrostatic pressure condition, where we can, when there is no flow, the water will always stay at the same level irrespective of the depth. Okay, but when it comes, how about the water table when it comes to a fine grained soil? The fine grained soil, always there is an action called surface tension which affects the amount of water to rise. That is why capillary rise will take place. This capillary rise is a negative force. Why? Because it is pushing the water to rise against the atmosphere. So against the water level will rise to certain extent. That particular rise is called capillary rise. We can expect that in fine grained soil. If the water table is at a depth of dW, if the water table which is present for some amount of depth, the pore pressure at fine grained soil will always be negative pore pressure. And if it is at a depth Z, that is below the water level, you can observe here, if it is below the ground level, then we can calculate the pore pressure by using unit weight into its height. Okay, so if it is a fine grained soil with having a negative pore pressure, which leads to the capillary rise, and we can calculate that by using, that is U0 equal to minus gamma W into dW, that is the depth of the rise we observe from the particular soil. And we can also calculate the pore pressure that is below the ground level or below the water table or below the water level, which is equal to its unit weight into depth. The height of, remember this, the height to which the soil remains saturated with negative pore pressure above the water table, it's called as capillary rise. How it will behave in terms of coarse grained soil? When it is a coarse grained soil, water will drain from the pores and air will therefore be present in the soil between the ground surface and the water table. The pore pressure above the water table can usually be ignored. Below the water table, the hydrostatic water pressure increases linearly with the depth with the water table to a depth of dW. Example, you see here, we can observe there is a linear variation of the pore pressure even in fine grained soil, but the origin which always move towards the negative side. But when it comes to a coarse grained soil, we can expect the linear variation of remember, coarse grained soil is also having a linear variation of the pore pressure in below the water level. Okay, above the water level, even though if it is a ground surface which is present above the water level, even though if it is at the origin or the positive side, it will be ignored. Okay, it will cause a very negligible amount of effect on the particular soil. That's why in coarse grained soil, the linear variation of hydrostatic pressure will be considered from the level of water. What example, if you are talking about coarse grained soil, if you are talking about fine grained soil, what happens if the layers which has been composed with the different types of soil layers? That particular table, if the water is present in different layers of the soil, it's called as perched water tables. If it is a perched water tables, then the distribution of the pore pressure will not be linear. It will not be linear. It will not start with origin. It will not move to the negative side. It is a non-linear curve we can obtain in perched water table. Remember that. Okay. Next one, I will be talking about the pressure head. So we have been talked about the total stress. We have been talking about the effective stress. We have been talking about the pore pressure. Next, I will be moving on to what you mean by exactly the total head and pressure head in a soil. Basically, when we talked about the pore pressure, we talked about the level, or we talked about the height of the particular water in the soil. Here I will be talking everything about what is pressure head, what is total head, what is the elevation bed, right? How to do that? Here you see, if you observe the two particular figure, the height of the water column in the pressure head will be considered as HW. The HW is differ for different things, right? To identify the significant difference in pore pressure at the different points, we need to eliminate the effect of the point's position. The important thing is always consider in pressure head or the total head, we have to consider everything with respect to some reference. So the first one, which has the amount of water which is present in the particular physiometric head, which is called the height of water. This height of water will always measured with respect to the reference that is called as datum. There is an elevation head. What is the elevation head? The elevation head will always be the height of the height between the datum head as well as from the level of water. Okay, so that is called the elevation head. So the elevation head, the HZ of a point is the height above the datum line The height above the datum of the water level in the standpipe is the total head. So to measure the total head, that is H equal to Hz plus Hw. What is Hz? It is the height from the datum line. What is Hw? It is the height of water which is available in the particular soil. So the total head will be equal to a combination of both the elevation head as well as the pressure head. The pressure head is Hw, the elevation head Hz. So the total H equal to Hw plus Hz. Okay. Next one, I will be, whenever I am talking about the amount of water which is available or the variation in head, so I want to talk about hydraulic gradient, because here is the parameter which basically influencing the pressure head, which basically influencing the total head. Right? What exactly mean by hydraulic gradient? A hydraulic gradient is the rate of change of the total head along the direction of the flow. Okay. Example, if you see here, if you observe both the diagram, there is a difference in both the diagrams. One is in first diagram, we can observe the amount of water level in both the piezometric head is same. Right? So in first one, it is H. In both the pipe, it is H. But when it comes to, when we look at the elevation head, it is Z1, it is Z2. But in the second case, due to the variation in the pressure head, due to the variation in the amount of water which is available on the standpipe, that is the pressure head variation, we can expect the water to flow from higher elevation to lower elevation. The water will flow from H2 minus H1. There is a difference in hydraulic head difference. When there is a difference, we can expect the water to flow from higher potential to the lower potential. If you look at the second diagram, the total heads are different. The hydraulic gradient we can expect to flow from H2 to H1. That is H2 minus H1 divided by delta S. Right? But why it is not happening in first case? Because the total heads is same. So we can see the water level is same in the first head. So now, when we know about pore water pressure, when we know about the total head, we have to know about Darcy law, because Darcy is the one who has been related the hydraulic gradient with the hydraulic gradient with the permeability of the soil. So what do you mean by Darcy law? Darcy law says that the rate of flow of water through the cross-sectional area A is found to be directly proportional to hydraulic gradient. So the amount of water which flows from one point to another point through some cross-sectional area, where we can expect the water, that is the velocity of the flow will always vary with this hydraulic gradient. What is this hydraulic gradient? That is which is equal to change in area with respect to the height of the water. We can see here the point where the water is moving from point A to point B, where the elevation it is delta H and the area is delta S. Right? The flow of water, the velocity of the flow of water is basically depends on V is directly proportional to hydraulic gradient, which is directly influenced by the discharge as well as area of the water. How to get the hydraulic gradient? To get the hydraulic gradient, we have to observe the difference in elevation between the two piezometric head with respect to its area. Right? The coefficient of permeability of a soil is the measure of the conductance that it provides to the flow of water through its pore. Basically, permeability, the coefficient of permeability can be defined as, it is a conductance which is against the resistance of the soil. Right? So next one, this is the important when we have to remember. So many times I have been asked regarding the relationship between the water ratio as well as permeability. Permeability of all the soils is strongly influenced by the density of packing, because we observe that when the soil is at the dry side of the optimum, it has a higher amount of permeability compared to the wet side of optimum. So it has been greatly influenced by the density of packing, because in the lower density or in the dry of optimum, the void ratio will be comparably high compared to wet of optimum. Right? But how to relate both void ratio and permeability? For that, Hassan has given an equation for a sand. For a filtered sand, if the permeability is found to be 0.01 into D10 to the D10 whole square meter per second, D10, which basically indicates that we have been studied in the last class, which says that the effective diameter of the 10% finer particle, where D10 is effective particle size of mm, in mm, the relationship which is given by Asin is K equal to 1 by K naught KT into SS whole square into E cube by 1 plus E into gamma W by eta. Eta is basically related to eta is basically related to the thermal efficiency of the soil, and when it comes to E, which is related to the void ratio, SS is related to the specific surface area of the particle, right? So if the viscosity, if they have given anything which is related to viscosity of the pore water, if the question has been asked regarding viscosity of the pore water, then we have to use the same equation which has given by Asin, which is K equal to C into E3 by 1 plus E, which is approximately equal to C into E power whole square. Okay. For clay soil, we cannot apply the same equation for a clay soil. For clay, to get the desired amount of the relationship between the void ratio and permeability in clay soil, we have to use an equation log 10K, which is equal to E minus EK by CK. Okay, that is the equation we have to use. Next, the another important parameter is seepage velocity. What exactly mean by a seepage velocity? The velocity which takes place due to the seepage of water, which is called as seepage velocity, or the rate of flow, the volume of flow rate, which has been, it is the product of the velocity, flow velocity, and the total cross-sectional area, or we can also call it as, it is the velocity of the seepage water, which is called as seepage velocity. We can be easily determined by using the total quantity, which is equal to, say, flow velocity into particular area of the section. Next, at particular level, the water follows its own tortuous path through the pores. The average velocity at which the water flows through the pore scene is the ratio of volume of rate of average area of the voids, that is AV, and it has been called as the seepage velocity. What exactly mean by a seepage velocity? The seepage velocity is all about, remember, it is the amount of water loss we can expect through the seepage in a particular amount of area is called as seepage velocity. The porosity of a soil is related to volume fraction of the void. When you relate the porosity to the volume of voids, we know that porosity equal to volume of voids by the total volume, which approximately equal to the area of voids by the total area. We can relate that, right? So it can be measured in, the seepage velocity is also can be measured in laboratory by injecting a dye or a color pigment or a potassium permanganate into the seeping pore water, and if you note down the timing, you can observe the amount of and the flow and the flow path, flow nets of all the soil. Okay, that we can do in a lab. Next one, when it comes to the measurement of permeability, how to measure the permeability? Permeability can be measured in lab as well as in field, as well as through the indirect method. In laboratory, we know that this permeability has been measured by applying a Darcy law, which says that the velocity is directly proportional to hydraulic gradient. The major important two tests are, one is the constant head permeability test, and another one is variable head permeability test. The constant head permeability test is all about maintaining the constant head throughout the experiment to allow the soil to completely saturate and allow it to flow. So then we are going to calculate what is the amount of permeability of the soil, which can be calculated by using K equal to QL by AHT, where Q indicates the amount of discharge which has been collected here, and L indicates the length of the soil, and A indicates the area, and H indicates what is the amount of water level, that is the hydraulic head, and T indicates the time taken. And it's the same way we know that we can calculate this in. And remember one thing, the constant head permeability test can be applicable for the coarse grained soil. But when it comes to a fine grained soil, the falling head permeability test plays an important role. Here, the amount of the head will be varied, constant head. Over there, their head has been constant. In falling head, the head of the particular experiment has been varied to determine the amount of permeability in a soil. Here, the permeability of the soil has been very less. The fine soil has been used to determine the permeability through the variable head permeability test, because this particular soil has low permeability compared to the coarse grained permeability test. Now, to determine the falling head permeability test, we can use to determine the coefficient of permeability by using K equal to 2.303 AL by 80 into log basin of H1 by H2 over there. Small a indicates the dia of the pipe or the hydraulic pipe. and L indicates the length of the sample, A indicates the area of the sample, T indicates the time, as well as H1 and H2 indicates the variation of the two different heads, right? The next one, the another one which we have to concentrate, that is the permeability. How the permeability will vary when there is a different layers of the soils are present. That is the stratification of the soil. The stratified soil permeability we can measure. So how to measure? If let's assume the soil, the ground layer, which has 4 different layers, the 4 different layers has the permeability, which is the flow, the permeability which is taken place in horizontal direction for 4 different layers, that is K1, K2, K3, K4 indicates the different permeability of the soil, along with the height, which indicates H1, H2, H3, and etc. up to Hn. If n number of layers are there, you can go to Hn and Kn, right? So next, how to calculate the permeability? To calculate the horizontal permeability, or the flow which is taken place parallel to the bedding plane, or parallel to the flow, or parallel to the layers, that all the things are same. So to calculate that, that is Kh equal to 1 by H into K1 into H1 plus K2 into H2, etc. up to Kn into Hn. So to calculate the permeability in a stratified soil when the flow is horizontal, or when the flow is parallel to the bedding plane or parallel to the layers, then it can be taken as Kh equal to 1 by H into K1 into H1 plus K2 into H2 plus etc. up to Kn, because whatever the total discharge which takes place at the end, it is a discharge which is taken place by each individual layer. So therefore, Q is equal to calculate the total discharge when the soil having a 4 different layers or n number of different layers with a different discharge, then you have to go for an equation. Q is equal to Q1 plus Q2 plus Q3 plus Qn, etc. Right? If the stratified soil having a permeability, if the layers have the permeability, the flow which is taken place perpendicular to the bedding plane, or if the flow is vertical to the bedding plane, then how to calculate the permeability? To calculate the permeability when the flow is vertical to the bedding plane, so then you have to go for Kv equal to H by H1 by K1 plus H2 by K2 plus etc. to Hn, where all the flow having the discharge will be equal to same. Okay, so but when it comes to horizontal permeability, when the flow takes place in the horizontal direction, discharge, we have to sum up the discharge. But when there is a permeability along the vertical direction, we have to go for the discharge in all the individual layers will be same. Remember it. The next one I will be move on to the flow net. What exactly mean by flow net? Flow net is basically a graphical representation of the flow which is taken place in the soil. So that is below the ground level, which is called as flow net, which basically represents the secondary Laplace equation or 2-dimensional Laplace equation. Flow nets are always, remember the word flow net. It is a net type of structure which is basically represented in graphical representation of the flow, which is called as flow net. How to represent it graphically, we'll see it. So, but some of the parameters we have to see, or we have to keep it in mind while drawing the flow net. The flow net had its own characteristics, like 2 orthogonal sets of the curve forms a flow net. Always the curve which are available in the flow lines, which are orthogonal sets of the curve, which is in orthogonal in shape. It's a curvilinear curve. And there will be 2 major important lines to form a flow net. One is if you want to form a net, we require 2 different types of line. One is horizontal line and the vertical line. The horizontal line, which basically in terms of curve shape, which is called as flow lines, which indicating the direction of the seepage flow along the hydraulic gradient. But what do you mean by equipotential line? Equipotential line, the potential is equal in all the points or at all the heads of the points, which is called equipotential line. And some of the characteristics we have to remind before going to draw the flow net, which is flow lines and equipotential both are orthogonal to each other because it is a net type structure, and the area between the 2 flow lines, which basically called as the flow channels, because if 2 are going parallel to each other, the area in between that, which is called as a flow channel. The rate of flow in a flow channel is always constant. Remember, the rate of flow in all the channels will be same. The flow cannot occur across the flow lines. Equipotential line is a line joining the points with the same head. The velocity of the flow is normal to the equipotential time, and the difference in head between the 2 equipotential line is called potential drop or an head loss. Remember, the difference in head between two equipotential line is called potential drop. If you look at the figure here, you see the flow lines are parallel to each other. The space between the any two flow lines is called as a flow path. All the flow lines, that is green color, and all the equipotential lines, that is the red color, which form say flow net over there. The flow lines as formed from permeable layer to permeable layer. That is, this is the topmost layer which indicates the ground surface, where the flow net flow lines has to pass from one permeable layer to another permeable layer, as well as equipotential line has to pass from one impermeable layer to impermeable layer. This black line indicates a sheet pile, and this red color indicates the impervious layer, and this indicates the water. This indicates the ground surface. Where the green color indicates the flow line and red colors indicates the equipotential line. The path between these two parallel flow lines is called flow channel, and these particular red lines called equipotential line, where if you insert any piezometer, right, what will happen? The pressure at all the points will be same. Okay, so that is the characteristics we have to remember. Next, for any problem, if you want to calculate what is the amount of total flow which is taken place through the flow net, we have to remember that is delta H equal to H by ND, and with NF is the flow channels. That is, we have to remember ND indicates the number of equipotential drops, NF indicates the number of flow line. What is the number of flow lines which is available here? What is the number of equipotential drops we can expect from the particular flow net? That we have to remember. To calculate the total flow rate with a unit weight or unit width, that is, to calculate the flow per unit width, that is Q equal to NF into KH by ND, which is equal to NF by ND into KH. Or to calculate the total quantity of flow net, that is Q equal to NF indicates the number of flow lines, ND indicates the number of equipotential drop, K indicates the permeability, H indicates the hydraulic drop. What happens if all the soils, whatever we are talking about, the flow net, if it is not homogeneous, if the two different types of layers, or if n number of layers which is available in the soil, how to calculate the flow net, right? To calculate the continuity of the velocity which is normal to the interface, which shows that we can calculate when the boundary condition of the soil, which has two layers of soil with two different permeability, we can go for an equation that is tan alpha 1 by tan alpha 2 equal to K1 by K2. Tan alpha 1 by tan alpha 2, which is equal to K1 by K2, is the boundary condition when two layers of the soil met the two different permeability. Here the soil which is having two different permeability, that is K1 and K2, with the two different kinds of layers, that is alpha 1 and alpha 2, met each other. So which can be calculated tan alpha 1 by tan alpha 2 equal to K1 by K2. Okay, the last and the important concept, it is called quick condition and piping. What do you mean by quick condition and piping? Quick condition or piping, which basically occurs in a dam. The quick condition which deals about the condition is quick. How it will happen when the soil has been completely lose its entire strength, the entire effective strength or the shear strength of the soil has been completely lost. That particular process is called as a quick condition. If the upward water pressure which is lift the soil to the enough extent by losing the effective stress to completely disappear. The effective stress will be zero when the soil is under the quick condition, and it has a 0% of capability to withstand the load. Okay, that condition is called quick condition, which basically the quick condition is occurs at a critical hydraulic gradient. But what is critical hydraulic gradient? Whatever the amount of the water which is available in the soil, it reaches to its maximum extent by allowing the seepage to completely flow through the soil. So that is called critical hydraulic gradient. In a critical gradient, when a soil reaches to a critical hydraulic gradient, the shear stress or shear strength of the soil will be equal to 0. When it is equal to 0, the hydraulic gradient will predominate and the pore pressure will predominate, leading to the complete loss of shear strength of the soil. So how to calculate the critical hydraulic gradient? To calculate the hydraulic critical gradient, that is IC equal to GS minus 1 by V. What is GS? Is the specific gravity of the soil minus 1 divided by volume of the particular soil. Or you can also calculate by using submerged unit weight by unit weight of the soil. Okay. So next, the one more condition which is called seepage force. What is seepage force? The force exerted due to the seepage of the particular pore water, which is called seepage force. How to calculate the seepage force? To calculate the seepage force, we have to go for using an equation which is equal to J equal to I into unit weight of water into B into L. What is B? B indicates the width of one flow net, and L indicates the length of the one flow net. Right? If it is an equivalent amount of seepage pressure in the direction of flow, then we can go for I into gamma into W. Okay, so that is regarding seepage flow. Here I comes to the last part of my talk, which is all about solving the problem which is based on the things we have been discussed in the previous case. So we have completely come up with the things which is called as first we have talked about the compaction, then we have talked about total stress, effective stress, pore water pressure, then we have come to talking about permeability of the soil. Then we talked about seepage analysis. So here I will be going in a reverse: seepage analysis, compaction, like that. So let me take these are the questions which has been already taken in a GATE exam from past 27 years, where I have been taken from a book where it has been sought out. So the first question, what is the first question which indicates? The first question says, along a periodic line in an earthen dam, the total head is constant but not zero. The total head is everywhere zero. The pressure head is everywhere zero. Along a periodic line in an earthen dam. What exactly mean by periodic line? Periodic line is all about the topmost layer of the seepage line. The topmost layer of the seepage line, where we can expect the pressure head to be equal to zero with respect to atmospheric pressure. So the answer for the first one, that is pressure head is everywhere is zero. So why it is that? Because we know that periodic line is the topmost seepage line we can expect in an earthen dam. Right? So what is the second one? The number of flow channels and the head drops is 4 and 12 respectively. If the difference in the upstream and downstream of the water level is 3 meter, what is the discharge per meter width of the sheet pile wall if K equal to 0.1 meter per second? What is the question here? They have given the flow channels are 4 and the potential head drops is 12, with the difference in upstream and downstream of the water level is 3 meter. What is the discharge per meter length of the sheet pile wall with K equal to 0.1 meter per second? So if you look at the diagram here, let me consider this diagram where they have been given a sheet pile has been inserted with a difference in water level from the upstream. Let me consider the left side as upstream and right side as the downstream. The upstream and downstream is having a hydraulic head, the difference is 3 meter, and also the number of flow lines are 4, the number of equipotential lines are, or the number of equipotential drops or equipotential head drops, which is 12. Then calculate the amount of the net discharge per meter length of the soil. So to calculate that, here you can see that is Q equal to NF into K into H. So what is Q? Q is the total discharge which occurs. What is K? K equal to permeability of the soil. They have given us 0.1 meter per second. H is the hydraulic head. We know that they have given a 3 meter. And NF is the number of flow lines. They have given 4. And N is the hydraulic drop, which has given 12 numbers. So if we substitute, the answer will get around 0.1 meter cube per hour. Or sorry, 0.1 meter cube per second per meter. So that is the answer you will get for the second question. What is the third question? Write the true or false in the answer book, saying that flow lines and equipotential lines in a flow net are orthogonal to each other. Definitely, when there is a flow net, the flow lines and equipotential lines are orthogonal to each other. So it is true. The next one, write the true or false in the answer book, saying that the water pressure is atmospheric at all points on a periodic line. Periodic line is therefore an equipotential line. No, it is not true, because periodic line is basically a topmost flow line which having a seepage path, but it cannot be zero. The atmospheric pressure at all the points in a periodic line cannot be zero. So that's why it's a false. So where is 5.5 here? So what is the 5.5? The hydraulic head at a point in the soil, which includes the hydraulic head at a point in the soil, which includes the pressure head as well as it basically includes the pressure head as well as the datum we saw here. So where we saw here, we have saw that here, right? So we know that in a particular any soil, the pressure head or total head, which always includes the datum head along with the pressure head. So that is the answer for fifth one. So next one, seepage force per unit volume can be expressed as seepage force per unit volume. So here we are going to representing the seepage force. To represent the seepage force, we know that we have to take anything with respect to hydraulic gradient with unit weight of water. So what is the answer? The answer will be taken as your hydraulic gradient with unit weight of water. Next one, the last one, that is 5.7, saying that peeping in soil occurs. When the peeping will occurs? When the soil which has reached the shear strength to 0. When it will reaches to 0, when the effective pressure becomes 0. You can see here the soil is highly porous, no problem. The sudden change in permeability occurs, no problem. But when the effective pressure becomes 0, the total stress will be 0. Then it will completely going to lose its complete shear strength. When it loses shear strength, then only we can expect the peeping to be happen or piping to be happen, right? So what is the next one? The soils most susceptible to liquefaction. When the liquefaction occurs, we know that the liquefaction occurs when there is the soil which reaches its critical hydraulic gradient with the quick condition. So basically this type of the condition we can expect in terms of the sands. So here what are the options they given? Saturated dense sand, saturated fine and medium sands of uniform particle size. So here, and saturated clays of uniform size, saturated gravels and cobalts. So here you see saturated clays of uniform size, definitely not. Saturated gravels and cobalts, definitely not. Quick sand condition cannot take place in that two particular case. But when it comes to the sand, here they have given two different types of sands. One is saturated dense sand, another one they are given as saturated fine and medium sands of uniform particular size. But here is the confusion that even though both are sands, why they are given uniform particle size? Because we know that when we have relate the particle size with respect to void ratio, if only the particle size having the same uniformity will always possess the maximum void ratio. So the expectable answer to be saturated fine and medium sands of uniform particle size. If the particle sizes varies, will possess small amount of resistance compared to uniform particle size of medium sand and medium sands and medium sands and fine sands. Okay, next one, the 5.9. What is 5.9? A proposed dam shown in figure is 90 meter long and the coefficient of permeability of the soil is 0.0013 meter per second. The quantity of water that will be lost per day by seepage. How to calculate the quantity of water? We can go for the same thing what we have done in the second question. We have done in the second questions that to calculate the amount of water which flows through the seepage per meter length of the soil by considering an equation of flow net, that is Q equal to KH into NF by ND, where K indicates the permeability of the soil. Here you see they have given 90 meter long head over there. 90 meter long dam. It is a 90 meter long dam over there. The hydraulic head will be vary from the water level, and the upstream side is 9.6 meter and the downstream side which is 9 meter. Why? Because the 0.6 meter of the water is present on the downstream side. So H equal to 9 meter. And the coefficient of permeability they are given as 0.0013 mm per second. So convert it into meter per second. Length is 90 meter they are given. Then NF and ND. So how many number of flow lines and equipotential lines which are present in the particular diagram? So here you see 1, 2, 3, 4. Four flow lines which are available in the first one. Whenever we are calculating the number of flow lines and equipotential drop in the particular flow net, we have to add 1 because we will be always missing the 1. So that is the flow lines will be this first path is first flow line, second path is second one, third one, this is fourth one, and this is fifth one. So total number of flow lines, that is 1, 2, 3, 4, 5, because this is a path. Okay, even though the number of lines are 4, we have to take the 5 is the number of path, NF equal to 5. What is the number of equipotential lines? The equipotential lines are 1, 2, 3, 4, 5, 6, 7. So if the number of equipotential lines are 7, then definitely the equipotential drop will be 8 in numbers. So if you calculate, and you can get the answer which is equal to 57. 57 is the answer you will get for this particular question. Okay. So next 5.10. So what is the specific gravity and in situ water ratio of a soil deposited 2.71 and 0.84? The value of the critical hydraulic gradient. How to calculate the critical hydraulic gradient? Just we saw that critical hydraulic gradient can be calculated by using IC equal to G minus 1 divided by 1 plus E. So the specific gravity they have given, the water ratio they have given, you can easily calculate what is the amount of critical hydraulic gradient. So the answer for this will be 0.90, right? So let me take the another different types of question or another topic. Before moving to that, one more question I will take here. The figure shows below have two flow lines for seepage, okay, and the interface between the two soil media for different permeabilities. Here you see there are two different types of soil layers are there with two different permeability. So K1, K2, alpha 1 and alpha 2. We have been saw that to calculate the amount of permeability when two different boundary conditions are arises, we know that we can calculate by using tan alpha 1 by tan alpha 2 equal to K1 by K2. Then you can get an answer which is equal to 66.59 degree. That is. So I'm running out of time. So let me move on to the second topic, that is compaction. What is compaction? The compaction we have been studied throughout. So here, let me take some of the questions. The unit weight of the soil at 0 air voids, which is basically depends on what? The unit weight of the soil at 0 air voids. When the soil is at the 0 air void condition, it basically depends on specific gravity, water content, unit weight of water, all the above, because we know that gamma D equal to G into gamma W divided by 1 plus WG, where we can relate the specific gravity, we can relate the unit weight of water as well as the water content. So the answer is the all of the above. Right? True or false in the answer book. The measure of the compaction is its wet density. No, it's false, because the compaction has been measured with respect to dry density of the soil. In a compaction test, the compaction effort is increased, the optimum moisture content will decrease, because we observe through the graph, right? Here is the 6.5. Compaction of an embankment carried out, it's a problem over there. Embankment is carried out 500 mm thick layers. The rammer is usually compaction has a foot area of 0.05 meter square, and the energy compacted in every drop of the hammer is 400 Newton per meter, assuming 50% more energy in each pass over the compacted area due to overlap. The number of passes required to develop the compactive energy equivalent to Indian standard light compaction for each layer would be. So here what they have given, they have given a condition where we have to reduce the amount of compaction which has been taken place to the Indian standard light compaction. Indian standard light compaction means we have to go for Indian standard Proctor test. What is standard Proctor test? Has a capacity of 259.1 kilojoule per meter of energy. How to convert it? We can convert by taking initially what we have to do. Initially we have to calculate what is the amount of the maximum dry density we can obtain, that number of layers, and then take the amount of energy from the standard Proctor test. What are the number of layers which has been used? What is the number of compacted effort has been given? Then compare both, you will get the answer. Next one is what is this? Compaction by vibratory roller is the best method of compaction in case of which one? Vibratory roller. Basically, whenever they have given a vibration to compact, it is always, remember, it is for sand. Because if it is the soil which has some cohesion, then vibration will not work. But if you take a sand in your hand and if you just vibrate it, the sand will go into compact. But if you take a soil and if you just shake it on your hand, the soil will not compact. So always remember the vibration will given for a sand. So what is the question here? They have given compaction by vibratory roller is the best method of compaction in case of moisty, silty sand, well-graded dry sand. Well-graded dry sand is an answer, because clay is not, silt is not, moist, silty sand. Here is also silt is there. But here when it is dry sand, example, you check it. If you take some amount of sand in your hand and if you just vibrate it, you will get the particular compaction through the particular method. So deposit with next one, that is 6.9. Deposit with flocculated structure is formed when the clay particles settle on a seabed. Basically what happens, the deposits with flocculated structure, we know that the flocculated structure which has been taken for basically for the fine grain soil, that is clay and silt. So here there are two clay options that have been given. One is clay particles settle on seabed, another one clay particles settle on freshwater lake bed. Basically this particular thing will happen when the clay particles settle on a seabed due to the attraction between the salt as well as the attractional force between the water which is present in between the soil particle. So let me take one more last question in compaction, because I'm getting my time up. So in a compaction test, G, W, S, and E represent the specific gravity, water content, and degree of saturation and void ratio of the soil sample. So respectively, if gamma W represents the unit weight of the water, gamma D represents the dry weight of the soil, the equation for zero air voids, which is equal to, we know that gamma D equal to G into gamma W divided by 1 plus WG. So I'm going to wind up this because I want to hand over my session to the next speaker. So with this, I will be stopping the second session and I'm hand over to our MC Rajit sir. Thank you, Rajit sir. Thank you, everybody.
Thank you, Professor Chethan. It was a very informative session. So I request all the participants to find the feedback link and provide your valuable feedback for the today's session. And also I request all the participants to join us for the second session at 3:45 p.m. using the same YouTube channel. Thank you.
Thank you.